Okay, so what are we going to do today? We have done in class 11, we had done the achievements of the long form periodic table, and we also did the defects of the long form of the periodic table. Now our today's topic is atomic properties or periodic properties of elements. Atomic properties or periodic properties. Okay. Now in this case we have already studied one statement that the properties of the elements, they are a periodic function of their atomic number, which was stated as a modern periodic law. When we will look at these properties, we will see that after regular intervals, the properties, they keep on showing a general gradation, or they have similar kind of properties. Like if we are talking of chemical properties, then after regular intervals, the elements, they will possess the same chemical properties, right? So we are going to study two types of properties. One is the physical properties and the chemical properties. Physical properties will remain same, chemical properties will remain same, whereas the physical properties, they will show a normal or a general gradation. The physical properties can be classified into two. Physical properties, they can be classified into two. The first one, they are known as individual. The first one will be known as individual properties. Individual properties or properties of individual atoms are those properties which depend upon the atom alone. For example, we have atomic and ionic radii. We have atomic and ionic radii. Then we have ionization energy. We will study electron gain enthalpy. Okay, and then we have valency. So all these, they are going to be the properties of individual atoms. The second type of properties which we are going to study, they are properties of group atoms, right? When we are talking of properties of group atoms, the properties which we will study under this are going to be melting points, boiling points, okay? And then apart from this, we have heat of fusion, heat of vaporization, heat of vaporization, etc. So these are the properties of group atoms. When we are taking a lot of, you can say, compounds, or we are taking group of atoms together, then these are the properties of group atoms. Like when we are talking of boiling point, we are going to talk of water, right? If we're talking of melting points, again melting point is that of water. So water is a group of atoms. Okay, so these are the two types of properties. Now all these properties, directly or indirectly, they are going to depend upon one factor, which is the electronic configuration. Electronic configuration has a big role to play when we are going to talk about periodicity in the properties. Why? Because in electronic configuration, the electrons, they are arranged according to various principles which we have already done. That is Aufbau principle, then we discussed the Pauli's exclusion principle, and then we did the Hans rule of maximum multiplicity, right? Now basically we say that why do properties have the properties are same after regular intervals, that is because of periodicity, which we have already discussed. Okay, so when we're talking of periodicity in properties, let's understand it in a little more detail. Periodicity in properties. Periodicity in properties is the, you can say that is basically, if you're defining is, it is what? It is the occurrence of same elements, same properties after regular intervals. After regular intervals in the periodic table, that is known as periodicity of properties, right? So this periodicity will occur after regular intervals after a definite pattern of atomic number. Okay, so this is what periodicity in properties is. Now, what is the cause of periodicity over here? The cause of periodicity is similar electronic configuration of atoms in their outermost shell after regular intervals. After regular intervals, that is the cause of periodicity. Okay, so after regular intervals we say that we have the same electronic configuration in the outermost shell. That is why the chemical properties after regular intervals, that is going to be same. Okay, that is the cause of periodicity. Now when we are talking of electronic configuration, there are many you can say properties which are going to depend upon electronic configuration, like for example screening effect, atomic size, ionization energy, electron gain enthalpy. So these are the properties which will depend upon the electronic configuration of the elements, right? Now chemical properties, as we just said, however, they are going to remain same due to similar electronic configuration in the outermost shell. Like for example, if you are talking of alkali metals, right? So alkali metals means lithium, sodium, potassium, rubidium, cesium, all these, they have the general electronic configuration of NS1 in the outermost shell. Like in lithium it is 2s1, 3s1, 4s1, 5s1 and 6s1. Due to similar number of electrons in the outermost shell and the similar electronic configuration in the outermost shell, all the alkali metals, they are going to possess the same chemical properties, right? So physical properties and chemical properties, the physical properties, they also depend upon the electronic configuration, but they will show a gradation, whereas chemical properties, they are going to be same. So the first property which we are going to discuss is the screening or the shielding effect. The screening or the shielding effect. The screening or shielding effect. What do we understand by screening or shielding effect? Now let's take an example over here. We are enjoying a bonfire. Okay, so let's say that in the center there is a big log of wood where we are enjoying a bonfire. So people, they are sitting in circles. This is the first circle, right? We say that over here there are 4 people, or let's say 5 people who are sitting in a circle. Okay, according to the space. Now when we take the next circle, you can see that the circumference of the circle has increased. So the number of chairs which can be adjusted here would be more. Okay, so let's say now we have 3, 4, 5, 6, 7, 8, 9 and 10 chairs which we have put over here. Okay, now there are still few people who need to be adjusted, so we draw one more circle. Okay, now what will happen? First of all, the people who are sitting in the first circle, they have the major effect of this bonfire. Okay, they are enjoying the heat to the maximum. But when there are 10 people sitting over here, so if there is going to be one person somewhere over here, what is this? The people who are sitting in the inner circle, what they are going to do? They would not let the heat pass to this person who is sitting in the outermost circle. Okay, so this is what shielding effect is, right? So we can say what is shielding effect? When the inner electrons, when the inner electrons protect the, or you can also write shield, protect or shield or screen. That also you can use the word, protect the outer electrons, protect the outer electrons from the nuclear charge. Right? From the nuclear charge. This is known as what? This is known as the screening effect. That is, the effect of the nuclear charge does not reach the outermost electron or the outermost shell due to inner electrons. That is what shielding effect is. Now the magnitude of shielding effect, that will depend upon what? Magnitude of shielding effect depends, number 1, on the number of inner electrons, the number of inner electrons, right? More the number of inner electrons, more is going to be what? The shielding effect. The magnitude of shielding effect, that is going to be more, right? And then it also depends upon another thing, which is the, you can say, the screening constant or the shielding constant. Second, it depends upon shielding constant, and this shielding constant, that is denoted by sigma. Right? It's the magnitude of screening constant, that is sigma, that depends upon what? It depends upon, or it is calculated on the basis of a set of laws which are known as Slater's laws. Okay? The magnitude of sigma, that is calculated on the basis of Slater's laws. Now, according to Slater's law, we have a definite pattern of electronic configuration according to the law. So let's see how are we going to group the you can say subshells together while understanding the Slater's law. The first of all, we will have one S. Okay? Then in the second group we have 2S and 2P, right? Then in the third group we are going to have 3S and 3P. Then 3D, that is going to be alone. right? Then after 3D we have 4s and 4p. And 4d and 4f, they are kept in the same group. Okay. So in a similar manner we then have 5s, 5p. And then we have 5d, 5f, and then we have 6s, 6p, 6d and 6f and so on. Right? There is no 6f, you know, there is only 4f. So we just keep it in here. Okay, so we have 6s and 6p. There are certain norms which have to be followed to calculate sigma. So let's see what are those laws. The first one is, you can write down, in the first law we have electrons to the right of ns and p. Electrons to the right of ns and np group contributes nothing to sigma. ns np group contribute nothing to the screening constant, right? So all the electrons which are right to the right of the ns and p, they are going to contribute nothing. We will do examples also to make it more clear. Then the second statement is that all other electrons in the ns and p, right, is nothing is going to contribute. All other electrons present in ns and p group contribute to the extent of 0.35. Now these we are talking of electrons which are to the left of the electron. Electrons to the right of ns and p group, they contribute nothing, but those which are present to the left, all ns and p, they are going to contribute 0.35 except for one s. One s which contributes 0.30. Okay. Then number 3, all electrons in n-1 shell, all electrons in n-1 shell contribute 0.85. They are going to contribute 0.85, right? And all the electrons in the n-2 shell, they are going to contribute 1. Okay? Now these laws, that is the first, second, third and fourth points which we have done over here, they are only true for s and p electrons. Right? First, second, third, 4 points, that is only true for s and p electrons. For d and f, for d and f electrons, we follow another rule. In this case, the first to third remain the same, right? First to third, that is going to remain the same. But when we are going on to fourth and fifth, like you can see over here, that first and second remain same. That is, for first, anything to the right, that is not going to contribute anything. Second, anything to the left, ns and p will contribute 0.35 except for 1s which is 0.30. Okay? But when we are talking of n-1 shell and n-2 shell, we have another rule over here. All elements in the groups lying to the left of lying to the left of NT and NF. Right? NT and NF, they are going to contribute 1. They are going to contribute 1.0. Now let's calculate the shielding constants taking these rules into consideration. The first one, let's go on to a simple element, lithium, which is 2 and 1. This is going to be the electronic configuration. Okay, so 2 and 1 means the outermost electron is 1. Okay, to the left it is 2, right? So 2 means, where do we have to, this is 2 is n minus 1 shell. So in the n minus 1 shell, the contribution is 0.85. Right? So what is going to be the shielding constant over here? There are 2 electrons in the n minus 1 shell. So it is going to be, sigma is going to be 2 into 0.85. Okay? So that comes to 1.7. Okay? Let's take another example. We have sodium. The electronic configuration of sodium is 281. Right? 281. So how many electrons are there in the n minus 1 shell? 8. N minus 1 shell, there are 8 electrons. So sigma will be equal to 8 into 0.85 plus there are 2 electrons in the 1 shell, in the previous shell. So 2 into how much? N minus 2 shell. Contribution, that is going to be equal to 1. Okay. So how many? How many electrons are there? 2 into 1. Okay. So this comes to 8.8. So the shielding constant over here, that is 8.8. Then let's go on to potassium. This is the electronic configuration 2881. Okay, so we have in the n minus 1 shell we have 8, right? So sigma will be equal to 8 into 0.85. And n minus 2, they are going to be 10. 8 plus 2, 10. So 10 into 1. So what is going to be the shielding constant over here? That is 16.8. Right? So this is how we calculate the shielding constant. Greater the value of shielding constant, greater is going to be the screening effect. Right? So you can remember this thing. Now when we are talking of shielding effect, we come across another property which is known as the effective nuclear charge. All this, what we are doing over here, that is going to help you to understand the properties better. Okay, so we have the next one, which is effective nuclear charge. What do we understand by the term effective nuclear charge? Now, due to screening effect, what is going to happen? The valence electron that is going to experience less of nuclear charge due to screening constant. Because what did we study? That screening constant, or due to screening, what is going to happen? The nuclear charge is not going to you can say experience any attraction towards the outermost shell. Okay, so we say that due to screening effect, less attraction is felt by the valence electron. So this means that the nuclear charge that is going to decrease, isn't it? If there is less attraction on the valence electrons, it means that nuclear charge decreases. Okay, so this decrease in nuclear charge or the nuclear charge after the shielding effect, that is now known as effective nuclear charge. Effective nuclear charge is the real charge or the real attraction which the valence electron that is experiencing due to the nuclear charge, right? So effective nuclear charge is always going to be a little lesser than the nuclear charge. Got it? So when we're talking of nuclear charge, the nuclear charge that is represented by capital Z, whereas effective nuclear charge is represented by Z star. Okay, so the nuclear charge over here, that is going to be equal to what? Effective nuclear charge minus the screening constant. Okay, so nuclear charge that is going to be equal to effective nuclear charge minus the screening constant. Now when we are talking of effective nuclear charge, it increases along a period. The effective nuclear charge keeps on increasing along a period, whereas when we are moving down the group, effective nuclear charge remains almost same. There is not much of a difference. So we have studied the basis of the rest of the properties which we are going to study in this chapter, which affect all these properties. That is number 1, the screening effect, and number 2, that is the effective nuclear charge. Okay. The first property which we are going to study is atomic radius or atomic size. Atomic radius or atomic size. Right? Now, when we are talking of an atom, we have been studying an atom and we assume that atom is spherical in shape. Okay? Because it is spherical in shape, that is why the word radius comes over here. Anything which is going to be a circle, we can measure the size by measuring the radius, or if we are talking it in 3 dimensions, we can measure the size of the sphere by again measuring the radius. But when we are talking of any atom, it is very difficult to calculate the exact radius of any atom. Okay, why this is happening? Before that, let's define what atomic radius is. So you can write down, atomic radius is the distance between the center of the nucleus between the center of the nucleus and outermost shell in which the electron is present. In which the electron is present. Okay? That is what the atomic radius is. Now when we are talking of atomic radius, as I just told you, it is not possible to calculate the exact value of atomic radius. That is due to 2 reasons. The first reason over here is that the atom does not have a boundary. ठीक है, the atom does not have a well defined boundary. Why? Because the electron cloud that is always diffused. Okay, because we are saying that as the probability of finding an electron is never zero. Okay, so it does not have a well-defined boundary as the probability of finding an electron is never zero. So if the probability of finding an electron is not zero, the atomic size extends itself up to that region where the electron is present. Okay, so we say that the electron cloud that is diffused, as a result of which it becomes very difficult for us to measure the exact size of an atom. Then the second point is that the size of atom is very small. Which makes it all the more difficult to isolate any atom and then measure the size. Okay, so because of these two reasons, we say that it is not possible to calculate the accurate or the exact radius of any atom. We generally calculate the atomic radius of atom in bonded form, not in isolated form. Okay, depending upon this, we are going to study different types of radii. The first one which we will study, that is the covalent radius. The first radius is covalent radius. Now, what is covalent radius? It is the 1/2 of the distance. One half of the distance between the center of nuclei of two covalently bonded atoms. Two covalently bonded atoms, right? So when we are talking of bonded atoms, bonded over here we are only considering single bonds, not double and triple. Okay? So if we have two atoms which are bonded like this, and let's say this is the center of one atom, this is the center of the other atom, and the distance is AB. Okay, let's say this is atom A, this is also atom A. So if you want to find the radius of atom A, that is going to be equal to the distance AB divided by 2. That is going to give us the distance. Okay, now generally when we are talking of this, we say that the covalent radius is mostly calculated for nonmetals. Covalent radius that will be calculated by for nonmetals. Okay. Now this is when we are talking of homonuclear or homoatomic molecules. Homo means we have written over here this is A and this is also A. But in case we say that we have heteroatomic. Now in case of heteronuclear, the diatomic DAB, let's say the distance that is going to be between the two different atoms, the distance is DAB. The distance DAB that is given by radius of A plus radius of B. Okay? Now if we know the distance AB, which can be studied by X-ray studies or by crystallography or by spectroscopy, we are studying the distance AB over here, and we have calculated the distance of A from this. Okay, distance AB we have measured, RA we have calculated from here. You can calculate the value of RB from here. This is the type of questions which come to you. Okay, we are saying that the distance for heteroatomic molecules, the distance AB, that is equal to the radius of A plus radius of B. Radius of A we have calculated from here, from homonuclear atoms, and DAB we already know, so you can calculate the radius of B. Okay, now if we say that there is a lot of electronegativity difference between the two heteronuclear atoms, so we are saying that if there is large difference of electronegativity, if there is large difference of electronegativity between the two atoms, then DAB, the distance DAB, that is equal to RA plus RB minus 0.09, this is a constant figure, 0.09 XA minus XB, okay, where XA and XB, they are electronegativities of elements A and B. Right? So now we have three methods to calculate the covalent radius. In the first method, it is simple. We take the mean of the distance or the average of the distance between the center of the two nuclei. If in case there are heteroatomic elements present, then the distance AB, that will be equal to RA plus RB. Okay? And if there are heteroatomic elements present but with a large difference in electronegativity, then we have to use this expression. DAB is equal to RA plus RB minus 0.09 into XA minus XB, where XA and XB, they are the electronegativities of elements or atoms A and B. Okay, let's take a few examples. For example, if we say that the distance of HH in hydrogen, that is equal to 0.74 angstroms. Right? Then what is going to be the radius of RH? That will be equal to 0.74 divided by 2. Okay? So that comes to how much? 0.37. Angstrom. Right? So the radius of hydrogen atom, that is taken to be 0.37. Let's take another example. We say that the distance between chlorine in chlorine molecule, that is 1.98 angstrom. Then what is going to be R of Cl? 1.98 divided by 2. So that is going to be 0.99 angstrom. Okay. Now if we have, let's take the example of an element or a compound which is carborundum. Carborundum is basically a compound of silicon and carbon, silicon carbide. That is what carborundum is. Now in this case, the distance SI and C, that is going to be equal to radius of silicon plus radius of carbon. This is the formula because it is heteroatomic in nature. Okay. Now the distance between silicon and carbon, that is 1.93. Right? And the distance and the radius of carbon, that is calculated to be 0.77. So what is going to be the radius of silicon? That is going to be 1.16. That is, radius of silicon is equal to 1.93 minus 0.77. So that is 1.16 Armstrong. Clear? So this is important because this is the kind of questions which we can expect over here. Okay, clear? Now when we are talking of over here, we have only spoken of single bond. Let's calculate the radius if there is a double bond present. Now if there is a double bond present, like when we are talking of single bond of carbon-carbon, we say that the distance, that is 1.34 Armstrong. So the radius of carbon over here, that will become equal to 1.34 divided by 7. Sorry, not 1.34, 1.54. 1.54 divided by 2. So that comes to 0.77. Okay. Now if we are considering C double bond C, it is seen that the distance that is reduced to 1.33. So in this case, the radius of carbon, that will be 1.33 divided by 2. So it comes to 0.665. Okay. Now if we have triple bond. Okay, so for triple bond, the distance, that is 1.20. Then what is going to be the radius of carbon over here? That is going to be equal to 1.20 divided by 2. Okay, so ये क्या आ जाएगा? 0.6 है ना? और 0.60 Armstrong. So this is how you calculate it for single and double bond. So this was the first kind of radius which we did. That was the covalent radius, which is more popular with the non-metals. Okay. The second type of radius which we are going to consider is the crystal radius. Now this crystal radius, that is going to be present in metals. Crystal radius, that is going to be present in metals. Now when we are talking of crystal radius, you can write down, it is defined as the 1/2 distance distance between the nuclei of two adjacent metal atoms in a metallic crystal. Metal atoms in a metallic crystal. Okay. Now metal atoms over here, we know that we have studied in the solid state that the metal atoms, they have a fixed coordination number. Okay. So in the metallic crystal also there is going to be a fixed coordination number, and mostly the coordination number which we consider over here is that of 12. Okay, like for example when we are talking of sodium chloride. So in sodium chloride, sodium has a coordination number of 6. In a similar manner, chlorine also has a coordination number of 6. Clear? So this is what a crystal radius is. Like for example, if we have a distance between two adjacent atoms of potassium in solid potassium, we are only having potassium. So what are we considering over here? We are considering a crystal of solid potassium. Now metallic radius, let's say that the distance between this two potassium atoms, that is equal to 4.62 angstroms. Then what is going to be the radius of K? That is going to be 4.62 divided by 2. Okay? So that comes to 2.31 angstrom. So this is the second type of radius which we have. The third type of radius, that is the van der Waals radius. Now van der Waals radius is what? It is the half of distance between nuclei of two non-bonding neighboring atoms of two adjacent molecules. So in this case, if we have one molecule over here, right, and we have another molecule over here. So if we are taking the distance between the two as this, then this is going to give us the atomic radius, the half of this. ठीक है? So ये वाला जो radius हुआ, that is going to be the atomic radius. Van der Waals radius is the half of the distance between the two adjacent atoms of non-bonded molecules. There is no bonding between this. So when we are talking of van der Waals radius over here, this is going to be the van der Waals radius. Have you understood the difference? This is the van der Waals difference. So now if you are comparing the sizes of all, it is said that van der Waals distance or van der Waals radius is maximum. Then after that is the crystal radius, okay? And after that is the covalent radius. So the size of covalent radius is the smallest amongst all. Okay? Clear ho gaya? Okay. Then let's do the variation in the period and in a group. The variation in a period. Variation in a period. We say that when we are traveling from left to right in a period, the nuclear charge increases, right? And the electrons, they are fed in the same shell. When the nuclear charge will keep on increasing, what is going to happen is that the outermost shell would be attracted by greatest force. As a result of which, a longer period when we are traveling, the atomic size keeps on decreasing. Okay? So if we are taking the second period, elements of the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. the size that will keep on decreasing. Lithium will have the largest size, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. But when from fluorine we go to neon, we see that there is an increase in size. Why this is happening? Because in neon or all the noble gases, van der Waals forces are present. Okay, van der Waals forces, they are going to be present, therefore the size increases, otherwise the size keeps on decreasing. Then second is variation down the group. The size of atoms keeps on increasing down the group. Why this is happening? This is happening because of introduction of a new principal shell. Okay? So if we are going down the group, in case of alkali metals, we have lithium, sodium, potassium, rubidium and cesium. Francium is radioactive, so let's not study about francium over here. From lithium, we are filling up 2s1, 3s1, 4s1, 5s1 and 6s1. So as the shell size is increasing, we are introducing a new principal shell over here, the size will also increase. So this is how the size that would increase over here. Okay, so when we are looking at the atomic sizes, let's just write some concluding points. Conclusions. Number 1. Alkali metals have the largest size in the periodic table. Atomic metals have the largest size in the periodic tables and the halogens have the smallest size. Okay, alkali metals will have the largest and halogens they will have the smallest. Then the inert gases, they have large size. I have already told you. Inert gases will have large size due to presence of van der Waals radius. Okay, due to presence of van der Waals radius. Okay, now when we go on to the transition series, because we have not discussed the transition series over here. In transition series, there is an irregular decrease or increase in the atomic size. Why? Because of screening effect. Okay, so in this you can write down that in transition series, the decrease in size is very small because of screening effect. Because of screening effect. Okay, so today we will do only till here, right? Tomorrow we will do the next property, that is the ionization energy and electron gain enthalpy. Two properties we will discuss in the next lecture.